Please, Clay, you can start.
Okay, thank you very much, and thanks for all the students for hanging in there and coming to the last lecture. So when last we met, we were talking about various different background fields that we can use to probe different notions of global symmetry, and I emphasized for you the fact that if you have a Q-form global symmetry, which is discrete, then there is a discrete cohomology class bracket B in HQ plus 1 of your spacetime manifold, which is characterizing the possible background fields, the gauge equivalence classes of background fields, and that these things are characterized by holonomies. Now, this sounds quite abstract, I think, for many of you. So what I would like to do for the first part of today's lecture is to zoom in on the example of SUN Yang-Mills and to tell you more explicitly what that background gauge field is in SUN Yang-Mills.
Recording in progress.
Okay. So we're going to consider 4D SUN Yang-Mills. I remind you the global form of the group matters for our discussion. And we saw that this meant there was a Zn one-form symmetry, and it was related to confinement. So apparently, this theory that we all know and love can be coupled to a background field B in H2 of our spacetime manifold with coefficients in Zn. So what is this B? That's our question. How would we actually explicitly understand what it means to study SUN Yang-Mills in the presence of a non-zero background B? And we'll see that this is closely related to bundle topology. So we'll focus in the beginning on a simple concrete case. We'd like to describe the difference between gauge bundles of SU2 versus SO3. So we'll begin with a kind of general discussion, then we'll see what it has to do with studying SUN Yang-Mills theory in the presence of a background field for the one-form symmetry. Okay, so the first thing we need to know is how do we label topologically SUN bundles, or SU2 bundles? These are labeled by an instanton number. So what's the instanton number? Let's call it I. It's equal to 1 over 8 pi squared integral over our spacetime manifold M of trace F wedge F. And this instanton number is an integer. So when we talk about the path integral for SU2 bundles, what does that actually look like? Or for SU2 gauge? Well, it has sort of two parts. The first part is an integral dA over all the gauges. So this is an integral over connections, of course, modulo gauge, on a fixed bundle. but then it also has sum over instanton number, I, which is in Z. So this is labeling the different topological types of bundles. So that's what it means. So of course we have, e to the minus s and whatever insertions, blah, 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 are in here. But what I'm emphasizing to you is that the measure for SU2 Yang-Mills has an integral over a certain continuous part, the connections on a fixed bundle, and a sum over a certain discrete part, which is the bundle topologies. Now I'd like to compare this to what's going on in SO3. So the first thing that one needs to remember is that SO3 has more gauge bundles than SU2. What I mean by that is that any SU2 bundle is an SO3 bundle, but the converse is not true. So in addition, to the instanton, there is now another invariant. This other invariant is the so-called second Stiefel-Whitney class. It is commonly denoted as W2. And what kind of object is it? It's a cohomology class in H2 of M with coefficients in Z2. So what is this? Some of you may have seen it before. Some of you may not have seen it before. You could think this is a Z2 valued magnetic flux. Meaning, if I take W2 and I evaluate it by integrating over any 2 cycle, then this is meaningful modulo 2. So it's a number that I can think of as either 0 or 1. Now, why do I say it's a magnetic flux? Why is it a Z2 valued magnetic flux? Well, there's a useful intuition about this, which comes from looking at a special case of a U1 subbundle inside SO3. So let's imagine, for instance, that A, okay, so we can write A is AA times sigma A over 2, where these are the Pauli matrices. So this is a general SO3 connection. So A equals 1, 2, 3. And if we say only A3 is not equal to 0. So this is inside the U1 diagonal subgroup generated by sigma 3 inside SO3. And then the claim is that, which is a little exercise. So the claim is that W2 equals the integral of dA3 over 2 pi. So W2 over sigma 2. So that's why I called it, here I take the answer mod 2. So that's why I call it a discrete magnetic flux. So you take the magnetic flux, the usual thing you would call the magnetic flux of the U1 subgroup, but you take it mod 2. And if you take it mod 2, then it's actually invariant of SO3. So, what happened to my mouse? There. there are several properties that we would like to note here. So, okay, I guess an exercise, this you should check. This is not actually that hard to work out. Now, one general property that we would like to note is that if the bundle is in fact an SU2 bundle, that implies that W2 equals 0 as a cohomology class. So we have, this is what I meant when I said that SO3 has more gauge bundles. In addition to the instanton number, we also have this, this second Stiefel-Whitney class. And so we can put this together and look at the SO3 integral. So what would it like? So just as in the SU2 case, we have an integral over connections. We have a sum over instanton numbers. And we also now have a sum over W2, where I remind you that W2 is in H2 of your spacetime manifold with coefficients in Z2. So I is an integer, but W2 is summed over this cohomology group, whatever it happens to be. And then, of course, we have e to the minus s and whatever insertions we have here. So notice here the difference between the SU2 gauge theory and the SO3 gauge theory. In the SO3 theory, we have an additional sum to do. Sum over more bundles.
There's a question.
Yeah.
George, please.
So in general, how do we know kind of if we've exhausted the list of topological invariants for a given gauge bundle? Like if we wrote down SU2, okay, sure, we have the instanton number, then we write down SO3 and we have another one. Is there some situation in which for a higher rank bundle, we might end up with more topological invariants? I mean, how do we know that we've listed all the sums that we need to do?
Yeah, good question. So, so to rephrase the question a little bit, the question is, how do we figure out all topological types of bundles so that we do the right sum? And this is a subject in mathematics that was basically solved in 50 years ago, maybe more. So from our point of view, we learned those results, basically. And I will try to quote them authentically to you. But let me just say that there's not a mystery here for us to figure out. There's just something, a kind of piece of knowledge that we need to have. Any other questions? Okay. So what's going on in the SUN story? The SUN story is similar. So SUN topologically labeled by a single integer instanton number. Meanwhile, SUN modulo Zn, this is really what we were doing before for the case n equals 2, where SO3 is SU mod Z2. These have an additional invariant. The additional invariant is a class W2 in H2 of M with coefficients in Zn. And the SU2 or SUN rather mod Zn path integral includes a sum over W2. So coming back to the question that was asked, for SUN, this is the complete story for bundles on 4 manifolds. So we're doing gauge theory in 4 space-time dimensions here, and this will also work in lower dimensions. If you go to higher dimensions, so if you wanted to do gauge theory in 6 dimensions, why you would be so perverse, nobody knows. But if you wanted to do that, then there will be more invariants to study. Okay, so this was our little detour into what's going on in bundle topology. And you'll notice here that this group, H2 of MZN, this is precisely where the background fields that we were looking for, these B fields, were valued. So in fact, now I'll connect back and tell you what it means to do SUN gauge theory in the presence of a background B field. So now we're going to return to background for Zn1 in SUN Yang-Mills. So I'll write a formula for what Z of B is. The partition function for this theory as a function of B. So here this is in H2 of M with coefficients in Zn. So we're going to sum over instanton numbers. We're going to, of course, integrate over the continuous part of the gauge field. We have our usual to the minus s, whatever insertions we want. But now, instead of summing over W2, we take W2 equals to B fixed. Not summed over. This is the definition. This is what it means to study SUN Yang-Mills theory in the presence of a background B field for the one-form global symmetry. So notice that the answer will be a function of B because B is not being summed over in this formula. So in case it is not clear from what I said before, these here, when we're summing over I, these are actually not S bundles anymore. They're SUN mod Zn bundles. Because W2 is equal to B, which is not in general 0. So that was our signature that we were in bundles for this other group. But we're not summing over all of them. We still sort of sum over the same number of them, just over I and Z, but not over W2. Any questions about this? Okay. So then we can continue and we can ask, well, what does it mean to gauge Zn1? First of all, what do I mean by this word? So what do I mean by this word? What I mean by this word is to sum over background fields. So we've already learned what it means to study the theory in the presence of a fixed background field. But what happens if we do the sum over B here? Well, summing over B, this reproduces exactly the SUN modulo Zn path integral. So what we learned from this is a rule for what happens when you gauge a one-form symmetry. So N Yang-Mills, this is really more general, so maybe I'll just say gauge theory. SUN gauge theory plus gauged Zn1. This is the same thing as what is normally meant by SUN mod Zn gauge theory. So you see that you can transition between different global forms of the gauge group by gauging some of the one-form symmetry. For instance, if we wanted to, maybe we don't want to gauge all of Zn, we could gauge a subgroup. Then we'd have a subgroup in the quotient here. Any questions?
Maybe I can ask a question. So this relation seems to be maybe not very intuitive because you have seems to have more stuff. The stuff on the left side is greater than the stuff on the right side.
The stuff on the left.
Well, because on the right you have your
which is the left? Is this the left? Is this what you mean?
Sorry, you're comparing SUN mod Zn gauge theory, right, with the SUN gauge theory and gauge Zn, right?
Yeah.
But on the right, since you're quotienting your group, it seems like you have less degrees of freedom, right? And then, but on the left, you're comparing SUN with something which seems like an additional stuff.
Yes, but this counterintuitive business, I agree that's a little counterintuitive, but it's not. It's the same. It's the same confusion that arises from this, where you say SO3 has more gauge bundles, right? So it's really that you're trying to wrap your head around there. That SO3 is SU2 mod Z2. But there are more ways for an SO3 bundle to be twisted than for an SU2 bundle. Right? I mean, maybe it's kind of a covariant versus contravariant thing. You know, the representations, there become fewer representations, but there become more bundles. In a sense, it's because bundles are like the magnetic part. So there are fewer representations, and so there are more things that satisfy Dirac quantization with respect to those representations. That's basically what we're seeing here.
Okay, yeah, it's a good example.
Okay.
I mean, sorry, just building on that question, like rephrasing it, can we say that since we have gauged the Zn1 symmetry, yeah, just this last line, that essentially, like in words, just means that the degrees of freedom which were related by the Zn1 transformation are now what we will call as equivalent, and hence on the right side we have SUN mod Zn gauge theory. It's combining those degrees of freedom into an equivalence class. Is that
that's correct?
Right,
yes,
words?
that's correct. Yeah, that's correct.
Okay, thanks.
Okay, since there's no more questions here, maybe I'll spend a little bit of time going over another basic example. Let's see. Let's go over another example of this formalism, because it's a little bit tricky when people see it the first time. Okay, let's do one more example. Let's do 3D U1 Loveday Chern-Simons theory. So the action is K over 4 pi A wedge dA. And I claim that this theory has ZK1 symmetry. Okay, so we'll go through this a little quickly. It's similar to the other examples that we've studied, but it's a good one to have sort of in your mind. So why does this theory have the symmetry? Well, you could say, the first thing you could say is, well, I'll measure the charges of Wilsons. Now, naively, this looked z-valued. Right? Naively, we can have a Wilson line of any electric charge. And, well, what does that mean? It means that you would naively think that you have a z-valued one-form symmetry. Now, we'll see that this, this reduction from z to zk is very similar to the reduction from screening that we already saw in other examples. So what is the screening effect to consider? So the screening effect is that we can consider a monopole operator. So this is an integral over S2 of F. And a monopole operator would be a configuration where this integral is not zero. Now, the Chern-Simons term, which of course is KADA written up here, you can think of this as saying that the monopole operators have charge K. And these are dynamical. We have to sum over such fluxes in the path integral. So what that means, following our general logic of screening, is that this U1 symmetry, which would have been naive from measuring the charges of Wilson lines, this is in fact broken to the true symmetry ZK1. So that's the true one-form symmetry of Chern-Simons theory. And okay, we could try to couple to a background field. How will we do that? Well, we'll take the action to be as before. But now we'll add a new term that looks like A wedge B, where this B, we think of it as being in H2 of our manifold with coefficients in ZK. So that's going to be our coupling to a background B field. This is Chern-Simons theory coupled to a background field for its one-form symmetry. Now, you could ask, how can I see at the level of this action the reduction to ZK? So let me go through that. So if we want to check the reduction to Z, we'll set big B equals to K times little b, where little b is properly quantized, meaning that the integral of little b over any manifold that this is an integer. And what I would like to show you is that this, if I consider such a big B field, then it will drop out of the path integral. So this will be equivalent to coupling to no gauge field. So what we do to achieve this is we write B, little b, as the curvature of a gauge field. We can always do this. So I'll write B equals dc. With C some gauge field. Notice that since B was properly quantized, C is a properly normalized gauge field. And now, change variables. In the path integral. From A to A minus C. What does the action look like after I do that? So S becomes K over pi integral of A minus C wedge d A minus C plus K over 2 pi A minus C wedge dc. So here I've used the relationship between big B and little b, and I've used that little b is equal to dc. So that's where I get this k, and that's why this looks like that. Okay, does anybody see what the next step should be?
There is a question or a
Okay.
comment from Taiwan.
I'm trying to see if anybody is still listening, so let's see.
Yeah. Taiwan.
What would it be to say that this action is invariant? So we'd have to compare this action to what you had before. Extract some condition on C, perhaps.
Extract some condition on C. That's a good guess. Remember, what are we trying to do? We're trying to show that this B field is equivalent to no B field at all. What does it mean to be equivalent to no B field at all? What kind of error are we allowed to make?
A gauge transformation.
We're allowed to make a gauge transformation error. We're allowed to make actually a bigger error than that. When you check that two actions are equivalent, what does it mean to say they're equivalent? Usually you're looking for separated points information to be equivalent. So what will happen is that if you change, if you modify the action by something that depends only on the sources, then that's actually okay, because something that depends only on the sources is a counter term. Okay, So I claim that this is the same as saying of k over 4 pi ADA minus k over 4 pi C dc. Here I'm using the fact that I can shift variables because I'm integrating over A. So this is the same. So B is zk valued. Modulo counter terms. That's this one here. This is the counter term. Okay, so I encourage you to think about this step. And maybe we can discuss it more in the discussion section about why this is why these kind of steps are legal. Okay. Okay, so I want to stop here, having done a few examples. So you have the summary is that you have several examples in your arsenal now. So what's the summary? The examples in your arsenal are, you know that U1 Yang-Mills in 4D has U1 1 electric and U1 1 magnetic, and you know what happens with matter. You know that SUN Yang-Mills has ZN one form symmetry. And it should be clear to you what happens with matter. Fundamental matter will break this whole thing. Matter in multi-tensor representations will break it down to whatever anality is the minimal one that you have. So what happens with matter? We also saw this is related to confinement. So that was about gauge theories without Trent-Simons terms. And then finally we saw that U1 level K, this has Trent-Simons has ZK one form symmetry. So what I'm teaching you here is that one form symmetry is ubiquitous in gauge theory. It's all over the place. And so it's not some fancy thing that you have to go hard, you have to look hard to find. It's really there in sort of the most basic gauge theories that we want to understand. And so that means that you're going to have to learn to deal with this tool. It's just fundamental. Okay. So in the last 20 minutes, I'd like to say something about anomalies. Some basic thing about anomalies and connect on to the discussion that we had in day one about the different dynamical behaviors of the infrared. So let's go back to thinking generally about the partition function. So here A is a background gauge field. For some global symmetry. Now, you can have in your mind two situations. One is that you can think that A is a background field for an ordinary, simple, continuous global symmetry, but you should also now have the seed in mind that A could also be a background field, something like what I was calling B before, a background field for a discrete symmetry or a higher form symmetry. Many of the properties will be similar. So in the simple continuous case, Z of A was the generating function for current correlation functions. And in that context, in correlations, J is conserved at separated points. So let's ask ourselves, what about contact terms? We just saw that in the Chern-Simons theory case, that the contact terms sometimes matter. So let's look at here. What about contact terms? So in other words, is J conserved at coincident points? So what I mean, this is, if we ask this about the partition function, it's the asking, is Z of A plus D lambda equal to Z of A? Is it gauge invariant? Now, of course, here I've written D lambda, so it evokes your thinking about an ordinary background gauge field, but each of the different types of background gauge fields that we went through for different notions of global symmetry have their own gauge transformations. And so you could think that this is a kind of stand-in for all possible gauge transformations that we could consider. Okay, so the answer to this question, is Z of A plus D lambda equal to Z of A, is in general no. In general, we can say something though. In general, we can write Z of A plus D lambda equals Z of A times a phase. I'll write the phase as omega of lambda and A. Now, I'd like to highlight one feature of this phase, omega. One feature is that this phase is local. It's local since the current is separated points. That's how you would see it in the continuous case. So remember, contact terms in the effective action give rise, so by that I mean local functions of the sources, give rise to delta functions and correlation functions, so coincident point corrections. And we know that we have a good global symmetry in this discussion, so we know that J is conserved at separated points. So what we know from that is the kind of error that we're allowed to make when checking gauge transformations is always of this general form, something local in the source and the gauge transformation parameter. Now, this is annoying, you might think at first sight, this is annoying. So we could try to adjust our definition of the partition function to remove it. To restore gauge invariance. What kind of adjustment is allowed? So take Z of A, and we can modify it by including in the action something that modifies correlators at coincident points. So this is a local counter. So as I have stressed above, such modifications change coincident point correlators. And any change in scheme can be parameterized by a choice of f. So you could think that this freedom to adjust f is the same thing as the freedom to change your scheme. Okay, so what is the definition then of an anomaly in this language? So omega cannot be eliminated by any f, there is an anomaly. So these are classified by kind of cohomology problem. So obviously by writing down f, any f doesn't need to be gauge invariant. We can do the gauge variation of f, and we might modify what omega is here. And so what we're asking is if we can choose f to completely eliminate omega, to make the partition function gauge invariant on the nose. If you cannot, you say there isn't a 't Hooft anomaly. This is a definition of this term, 't Hooft anomaly. And again, I've written things in a notation which evokes your familiar, say, U1 background gauge field A. But really, this whole discussion is completely general. It applies, the same logic applies for any kind of global symmetry, any kind of background fields. This is really the main definition of 't Hooft anomalies in general. Questions about this definition? Okay. So of course, there are many examples of this. The most basic example that everybody is familiar with is the triangle anomaly. So you have three currents, J, J, J. You have vinyl fermions. Psi alpha of charge. Let's give them an index I. Qi under U1. This J is the current for this U1. And you look at this triangle diagram, and you find that the divergence of the current goes like sum over I Qi cubed F wedge F. And this is the same as saying that at coincident points, J in the 3-point function, J, 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 the divergence of J is not equal to 0. So here, this is F is the background field curvature. Okay, why are we so interested in anomalies? The way I presented them, they seem more like a nuisance than really anything useful. And I'd like to leave you with a kind of fundamental result. And the lectures by saying that the concept of symmetry is important in RG flow because it is scale invariant. If you have a symmetry in the ultraviolet, you have it in the long distance physics as well. And in fact, the same is true for anomalies. So anomalies are RG invariant. And this is really the key reason why we're so interested in them. So I'd like to give you a kind of intuitive proof of this. It's not a completely rigorous argument, but it captures the spirit of what's going on. So let's consider the partition function z of a g. Again, A is a background gauge field for any type of global symmetry we might want. And G here is a background metric. So why introduce this background metric? The reason is that by investigating changing G's, so G goes to e to the sigma G, we probe long distances. So I can study the RG properties of the effective action or this QFT by studying the correlation functions or the partition function as a function of G scaled up by various factors. Now, what we'd like to do is we'd like to use something fundamental, which is called the Wess-Zumino consistency condition. What is the Wess-Zumino consistency condition? You take the partition function z of a g. You first take the variation with respect to lambda. So this lambda is the gauge parameters for the grounds. And then we take delta sigma of the above. So this is this sigma here is this sigma here. So this is the scale variation. So putting this all together, this whole thing is telling us about the scale variation, the scale dependence of the anomaly. Now, the Wess-Zumino consistency condition is the statement that these partial derivatives, these variational derivatives, commute. And that's because, these gauge variations are abelian. They don't have any non-abelian structure to them. So we can say that this is delta lambda. I should put a log here since we talk about the effect. Since I really the anomaly, I'll put the log. Remember that z of a plus d lambda is z of a times e to the anomalous variation. So that's why I want the log. So these variations commute. So I can write z of a g here, and now I've got the variations, but in the opposite order. So the left-hand side has what we want, the scale dependence of the anomaly. What's going on with the right-hand side? So it's delta lambda of some, and it's something that we can evaluate. When you take the sigma variation, it means you change the metric by this overall scale. We're working to first order in sigma. So any change in the metric is the same as an insertion of a stress tensor. And the change in the overall scale is the same as the insertion of the trace of the stress tensor. So this is the integral over our space-time manifold of the expectation value of the trace of the stress tensor. And we're supposed to take delta lambda of it. And the point is that this is 0. Why is it 0? This is because tensor should be gauge invariant. Should be invariant in global symmetry. So it shouldn't respond to taking the gauge variation. So this is what I wanted to show you. I wanted to show you that anomalies, 't Hooft anomalies in general, are renormalization group invariant. And this is a sketch of an argument for you. We see that the scale variation of the anomaly is 0 due to expected properties of the energy momentum tensor in quantum field theory. So this is why anomalies are so useful. It's because just like symmetry, there's something that you can compute in the ultraviolet, and it's conserved along the RG flow, no matter what strong coupling or other funny business happens. And so they can help you solve for the dynamics of quantum field theories. So now let's circle back to this different behaviors, different infrared behaviors that we talked about. So let's connect to our first discussion. So as should be familiar to you, the partition function z of A is typically non-local. And this is, why is this? It's because it encodes separated point correlation functions. Now, if a theory is trivially gapped, what happens? Remember, that was one of our possible, the simplest possible behavior that we could ask about the infrared. It meant there was a unique vacuum and everything else was massive, and there were no even topological correlation functions. Now, if a theory is trivially gapped, it means that all correlators are reduced to contact terms. Well, what does that mean in the language that we've been saying here? It means that for a trivially gapped theory, Z of A for any background gapped. This is the infrared effective action. It's just this, just this local function of sources. This is also sometimes called an invertible theory or a symmetry-protected topological theory. Those are all the same thing. So note now, from this, we conclude that a trivial gap theory has no anomaly. This is just by definition, because anomalies were all the things that we couldn't remove by adjusting the local counter terms. But here you see that in the infrared of trivially gapped theory, the whole effective action is a local counter term. So of course you can remove it, any anomaly, by adjusting the local counter terms. We can look at the contrapositive of this to get the conclusion in the form that is commonly invoked, which is that a theory with a non-zero 't Hooft anomaly cannot flow under RG to a trivially gapped theory. And this is really the fundamental conclusion that I wanted to get you to. Here we've combined the RG invariance with some basic observations about what it means for a quantum field theory to be really empty at long distances, to be this trivially gapped theory. What we see is that any time you have any ultraviolet, gauge theory, whatever, you find some anomaly, some 't Hooft anomaly, for any kind of symmetry that happens to exist, you know immediately that no matter what dynamics occurs, the theory cannot be trivially gapped at long distances. There has to be something pretty interesting there. Okay, so I'll leave you with that to take and use in your own studies of quantum field theory. Thank you.
Okay, thank you very much, Clay. So let us open our microphones and thank Clay for his wonderful set of lectures. This was the last lecture of Clay, and you will still be.
I'll be back in an hour, I think.
Back in an hour with the discussion session. So if there is any short questions, please raise your hand and ask them now. All right, I see no question. Okay, there is a question in the chat. Khan, can you, well, I think Khan cannot ask his question. So he's asking about the exact physical difference between Yang-Mills theories with SUN and SUN mod ZN.
Well, okay. Perhaps the most concrete thing to say is that, you know, the different topological things. Let's imagine we want to study this question at weak coupling. So where we sort of have the most control and we're trying to compare to our studies of gauge theory and perturbation theory. So as you know, the correlation functions in perturbation theory, or perhaps you don't know, those are sensitive only really to the trivial bundle. So those would be the same. But the different bundles that appear in the sum, those are what are commonly called the instanton sectors or the non-perturbative corrections. And so basically what I'm telling you is that the non-perturbative corrections in SUN and SUN mod ZN are different. So the exact analytic formulation function for the correlators are very different. In very small coupling, in small Yang-Mills coupling, this can look like a small effect because anyway, all the non-perturbative physics is small. But once you're at finite coupling or strong coupling at the QCD scale, then this matters a lot. So the infrared of these theories can be totally different.
Okay, thanks. There's a question from Antonio. Antonio, please.
So follow up on this. Can these things be checked, say, on the lattice, for example?
Sure. Yes.
And is there like some qualitative thing that one can learn? Like,
Well, you could ask, what is the I mean, for instance, let's go to maybe some lore about Yang-Mills theory. If I had one more lecture, I would have applied all this formalism to tell you something about the infrared of Yang-Mills theory. So pure SUN Yang-Mills theory is commonly believed to be trivially gapped at long distances in the discussion that we have had today. Now, meaning it's literally not just gapped, but there's not even any topological field theory there at long distances. Now you can ask, can the same thing be true, for instance, for SUN mod Zn? Naively, they look pretty similar. But what we've actually proven in the course of this discussion is that the same thing cannot be true. Because if SUN is trivially gapped, then SUN mod Zn will have kind of topological gauge theory, a Zn one-form gauge theory at long distances, where you to account for this change in the gauge group. So, you know, the infrared behavior is different, really different.
thanks.
So let me also ask a quick question. So we considered an example of triangle anomaly, right?
Yeah.
So what does it tell us about, you know, a theory in IR as being non-trivial gap? So what is the consequence in IR?
So yeah, so of course the theory, any theory with the triangle anomaly by this general conclusion cannot be trivially gapped. But in fact, you can do more with the triangle anomaly. So the triangle anomaly you can prove implies that a theory is gapless. And the reason is that you can prove that the triangle anomaly means that there is necessarily some power law behavior at separated points in the JJJ 3-point function. So a theory with the triangle anomaly not only is not trivially gapped, but it can't even be gapped. It has to be gapless. And so this is another kind of emerging topic in this theory, is to try and distinguish which anomalies allow for a mass gap. Maybe they can't allow for anything trivially gapped. Maybe they can be carried by topological field theory. And which anomalies necessitate something like a conformal field theory or a vanishing mass gap at long distances. And the triangle anomaly is in the latter camp.
Okay, thank you very much. I see no questions, so let us thank Clay once more. And we will reconvene in about 12 minutes. Yeah.
Okay.
Or with the discussion session.